So, welcome to strong field laser physics. Perhaps a brief reminder, well, perhaps not so brief reminder of what Matthias discussed last time. He started with recollision physics, and as you may remember, I started this entire course with a presentation on the characteristic effects of strong field laser physics. And as it turns out, all of these characteristic effects, these three characteristic effects, namely above threshold ionization plateau, high harmonic generation plateau, and non-sequential ionization, all of these have to do with this recollision phenomenon. Yeah? And therefore, a brief reminder on what we had in lecture 13. So, yeah, let's take a few notes. So, a reminder of lecture 13, so that we are all on the same page and then can continue with the discussion of individual phenomena. So, the first thing that we need is, when we speak of recollition, an electron that starts at some phase of the field. We call it T0. Well, I say phase of the field and say T0. What I mean more precisely would be omega times T0, right? But usually I just say T0, and most of the time I mean actually the phase. So the first thing that we need is the return time. When we start at T0, then if we speak about recollision, there should be a later time at which the electron returns, and we call it T1. And if we mean the phase, then strictly speaking, it would be omega T1. So that would be the first thing, just to define the nomenclature, what we mean by T1 and T0. So depending, yeah, that's nicer. Depending on T0, which is the burst time of the electron when it tunnels, you may say, certain trajectories return to the vicinity, of the core of the ion core at some time T1. Now the problem is, well, it's not a real problem, but the kind of complication is that it's of course a sinusoidal equation that describes this trajectory, and therefore we would have to find the zeros of a sinusoidal trajectory, which analytically won't easily work. Therefore, the straightforward thing would be to do it numerically. Yeah? So the function T1 as a function of T0 can easily be determined numerically. And I will show a respective plot in a second. So here it is. Well, I have to look for it. Here. So here it should come. Where is it? Yeah, here it is. And so what you see here is, first of all, just the oscillation of the field. So here we have the oscillation of the field in red, right, as also indicated here on the y-axis. And here with these dots in pink, yeah, so here we have T1 on this scale here. Yeah, so what it means is that if we start at the peak of the field, then it will take a full optical period. Yeah, so we measure this in units of the optical period, capital T. Then it will take a full optical period for the electron to return, which kind of makes sense, doesn't it? Right, so if you start at the peak of the field, then you will first accelerate it and then decelerate it, and it will return at this point. Yeah? Well, the other extreme is that we start here. Yeah? Then the electron will actually return immediately. Yeah? And therefore, you see here that the travel time, yeah, so T1 minus T0 is equal to 0. Matthias also explained to you in the last lecture that there is a nice graphical model that, or method rather, that reproduces that as well. Let me do that. Let me also repeat that. So this function T1 is, so this T1 as a function of T0 can also be determined graphically. Now, so we introduced this method, I think, back in 1995 in a paper in PhysRef-A, where we actually discussed two color fields and where this method can also be applied. So what do we do? So as quick figure for that. Yeah, so what you see here is the oscillating electric field. Well, to be precise, it's the integral. So it's the integration of the vector potential rather, right? And if we have an infinitely long pulse, then it is the same as the field disregarding a minus sign. Yeah, so I have drawn this field here as cosine-like, and therefore this f of t that was introduced last time is just minus that. But the sign actually doesn't play a role because we'll just find this some intersections with the axis. So now the point is, so just let's discuss the examples that I just gave. So we said when the electron comes out at 0, so when the electron comes out at this point here, then, and this is what this graphical method that was introduced last time has introduced, then we would take the tangent and look for the intersection of this tangent with this function f, or if you speak about an infinitely long pulse, then just the field itself, right? And we see exactly what we predicted, namely that T1 would be here if T0 is here, right? Same thing, of course, with this point here, but this is difficult to draw, and therefore I don't. Of course, the interesting things are not these special cases, but say a burst time, say here. Then we would also draw the tangent here, right? Something like this. I guess I have to shift it a little bit around. Yeah, so like this. And then, well, let me just delete the previous one. Yeah, and then this here would be T1, T0, excuse me. And we would have, at this intersection, we would have T1, right? Okay, yeah, so we see that this reproduces what we expect. Now, let's come to the subject of this lecture today. We will discuss the consequences, and actually, well, part of what I'm going to discuss was already introduced last time also, namely this famous 3.17 law. Yeah?
This recombination takes place as a function of the phase, right?
Yeah, so as I change T0, T1 will change.
Yeah, and that is as a function of the phase, like we throw
Yeah, so the question is whether the phase, I think, of the field would also change this scenario. Well, of course, you can shift it back and forth. The interesting thing, of course, evolves or happens when you take, say, a different field, say a two-color field, and you shift the relative phases of the two colors. But then you can still do this this method, because as the derivation has shown last time, it works for, so it works, analytically actually.
What is the time scale that really takes this process? Like how much time it takes to recombine?
How much time it takes to recombine, you said? I think the question is how much time it takes to recollide. Yeah, well, it depends, of course, on how quick the field oscillates. Yeah, so if we take the still usual optical period of a titanium sapphire laser, this is 2.5 femtoseconds, right? So then this here would be 2.5 femtoseconds. And so you see it takes a fraction of that, a good fraction of that. But of course, you can change the wavelengths, and then also this here changes. Now, let's discuss the consequences of this recollision, and I would start with high harmonics. Also, the emphasis of this lecture is actually non-sequential double ionization. So consequences, and these are the characteristic effects, the three characteristic effects. Yeah, because this 3.17 UP law also plays a role for non-sequential double ionization. Okay, so the first point here would be, and this is 541, high harmonic generation, more precisely the high harmonic generation cutoff. Yeah. So, and the idea there is that the electron that returns to the vicinity of the core, that this electron may recombine, and if this electron has some kinetic energy, then of course it may release a photon that corresponds to that kinetic energy plus the ionization energy. Yeah? So the electron returning to the core at T1 may recombine and emit a photon with a photon energy h bar omega equals to the kinetic energy, to the instantaneous kinetic energy at this point of time, namely at the time of return, plus the ionization threshold, right? And then the obvious question is, what is the maximum that we can do? Yeah, so what is the maximum kinetic energy? We won't change, of course, the ionization threshold of the atom. The question is, what's the maximum kinetic energy with which the electron can return? So, obvious question. What would be the maximum photon energy? Because high photon energies are high in demand. Yeah, so these would be precious photons. And what we do is that we apply our famous method, namely of conservation of canonical momentum. So conservation, we used it already in order to calculate the spectrum of direct electrons, so electrons that ionize without recollision. So we tried also here. So conservation of canonical momentum. And this means that we write the canonical momentum at different times. So in this case, just at time t, right? And it must be the same at any other time, in particular also at t equal to t0 plus EA of t0, right? And we use the strong field approximation. The strong field approximation says that the electron's initial velocity is 0, so this here is at least approximately 0, right? And then we use this here for t equal t1, and then we would write m times velocity at the time t1 is equal to the vector potential at time t0 minus the vector potential at time t1. Yeah? So that's our equation 1 for today. And, well, if we have the velocity, so I still write here momentum, but it's, of course, trivial to solve for the velocity. If we know the velocity, then we know the kinetic energy. Kinetic energy is 1/2 times mass times velocity squared. So the return energy, by definition, the return energy, I will call it E1, yeah? And it's defined as E, the kinetic energy, at t equals t1. Yeah, so this is the instantaneous kinetic energy. Yeah, so quite often when we speak about photoelectrons, we always mean the cycle averaged kinetic energy, Ponderomotive energy cycle averaged. All photoelectron spectra cycle average. But here we mean the instantaneous kinetic energy. So the return energy is the instantaneous actually, the notation already implies that. Yeah? So it's the instantaneous kinetic energy of the electron at the time of return, so meaning at t equals t1. Yeah? So, and then obviously we have E1 by definition should be 1/2 mv of t1 squared. And now if we just plug in equation 1, we get the result that was shown last time already, namely that it's basically the difference between the vector potential at T1 and T0. That's equation 2. Yeah, so we wanted to know the maximum of that. Yeah? So, and therefore, we might use again our graphical method in order to find the optimum. Well, let's actually have this picture once again. So this picture with the graphical method, in order to get the idea. So, look, what we want to have if we look at this equation. Yeah, so ideally, both would have the opposite sign, right? So ideally, this here would be the amplitude of this vector potential, right? And this here would be the negative amplitude of the vector potential. That would be definitely the maximum that's possible, right? More is not conceivable thinking, so looking at this equation. Then we would have actually two times the vector potential, right? For this hypothetical situation. So 2 times the vector potential. Now remember, the vector UP is given by 1/4 of the vector potential squared. Yeah? If we have here 2 times A, or A naught in order to speak about the amplitude, so I could actually draw that here. So this here would be the amplitude I denote A naught. So we would have here 2 times A naught squared gives 4 times, right? Which means, considering this factor 1/2, that the maximum, so the absolute maximum would be 8 UP. But you see, of course, that it's not possible to have an initial time. So to have a T0 here, and T1 here, this is actually not possible due to the restriction that both should be connected by a tangent. Yeah? So let me try to another approach to find that. So I still would demand that we return at this time here. Because then, at this time, if we return at this time, then we have here the maximum for this part, right? And then I would use the graphical method. Yeah? So I would start at this point here and then draw a line here that kisses f of t, right? And so I determine in this way, I determine T0, right? So now I've determined T0. So that's T0, right? And what we find is that we have here, well, what do we have here? Well, what we read off is something like 0.25 of A naught, right? So that seems to be a good estimate of what we can get. Okay, let's do that. So what we do is estimate E1 max So, and the procedure I have lined out. So we demand T1 or omega T1 equals 3 pi over 2 because this maximizes A of T1 in equation 2, right? Then we find T0 by the graphical method. By the graphical method. And what we find is something that is close, a T0 that's close to the maximum of the electric field, which is a good thing because this means that a lot of electrons are produced there, so the field strength is high. So we find a T0 close to a maximum, so this doesn't work really. So what has happened here? So we find a T0 close to a maximum of the laser field. And that's good. Because we get high ionization probability. But what's more important or equally important is we also find a value for A of T naught. We also find that A of T naught is approximately 0.25 of the amplitude of the vector field. So let's plug that stuff in. Right? So what we find is that E1 max is equal to E squared over 2m times 1.25 squared times A naught squared, and this is equal to 3.125 times A naught squared times divided by 4, or in other words, we find 1.2 times UP. Cool, right? The precise numerical analysis finds 3.17. Yep, we are pretty close by almost doing nothing. So this is pretty close. This is pretty close to the numerical result so if you would use this graph here above, right, and then plug in these pairs of T0 and T1 into our equation 2, right, then you can easily find just numerically the maximum, which is this famous number of 3.17 UP. Okay, so much for repeating what we had last time. Oh, I'm pretty late in time. But no problem, let's just continue. I think it's important. So we should do that. So 5.4.2, we want to talk about non-sequential double ionization.
So the energy maximum is the cutoff frequency. Is the energy at the cutoff at the end of the plateau in the high harmonic generation?
Yes, absolutely. Yeah? So the question was whether the energy cutoff is the end of the plateau, so the so-called cutoff in high harmonic generation. Absolutely. Of course, the 3.17 UP plus the ionization threshold, to be precise. Yeah? Okay, so let me start this with a little bit of literature, of a literature review. So, so maybe now it works. Yeah? So it starts with this famous paper here by Untitled. And what they found in France, so at that time, they built there the most powerful lasers. My pointer doesn't work. And what they found were surprisingly high charge states. So the title, multiply charged ions formed by multi-photon absorption processes. They did not really expect that they would observe a lot of krypton 3 plus, krypton 4 plus, and later they would even find higher charge states. And so in that paper, they were speculating about multiple excitation. Yeah, so that the entire electron cloud is somehow excited by the laser, right? Later, Untitled would write this paper here, and here you see for the first time, and it's really a pity that this thing here doesn't work. So I can't show it. So can I show it here with this thing here? No, it also doesn't show up. Here it is. So here I have a laser pointer, right? So what you see here, so this line here, this is a fit to what is expected from perturbation theory. So from the fact that so from the power law, so if you need n photons for ionization, then the number of ions should increase with the power of the intensity to the with the intensity to the nth power. And if you plot it on a double logarithmic plot, as you see it here, then you just would get a line with a slope, in this case, of n, right? And of course, you can do the same thing with the doubly charged ion, because you need more photons. The slope of this line is larger, but the interesting stuff is this, are these ions, right? Because if you continue that, then you see that there are excess ions at low intensity, right? So, and then Untitled made a clever analysis. So she said, I would use rate equations as you see it in equations 6a, 6b, 6c, right? And then the population, then the population of the neutral x0 would decrease with the population that you have in x0, right? So with the number of ions that you have, so x0 here is the number of neutral atoms. And of course, there is also the possibility here, and that's the interesting point, that you ionize directly from the ground state to the doubly charged state, right? And there's the corresponding cross-section for that, which is called sigma b, right? And I think the other ones are pretty clear. Yeah, so you have this set of coupled rate equations that can be solved. Yeah? Then came Peter Lampropoulos, and he wrote a very interesting paper. It's a little bit technical, I would say, but it gave a lot of insight at that time and resolved a lot of misunderstandings people had at that time. So there are basically two things that he explains there, namely what is known as saturation, namely once you have ionized all the atoms, which is actually, once you have ionized all the atoms, which is actually implicit already in the wave equations, then this here should saturate, right? Become horizontal, but it doesn't become horizontal. And Lampropoulos explained that the reason for that is that you have a large gas cloud, right? And you saturate them in the very center of the laser beam, but if the intensity is high enough, then the outer regions of the focus also get intense enough in order to ionize xenon, right? So what you see is volume expansion, right? For short, the volume effect. So Lampropoulos also pointed out that it's probably not an excitation of the entire cloud, but that you peel off electron by electron, right? And and what you see here in this figure 2 is actually a scaling of the cross sections, yeah, that he had from some other paper, which is cited here in the caption. And using this, very general and qualitative, so this very general scaling of cross sections, he actually doubted that this pathway B in Anlelier's analysis, that this is relevant. Yeah? So the cross section would be, in order to have that, the cross section wouldn't fit to this figure, right? So very worthwhile to read these two papers actually, even today. Okay, then another important paper, so now from 1992, almost 10 years later, yeah, by prominent figures, in particular Ken Kullander is a very prominent figure in strong field laser physics. David Fittinghoff, I never met him, but he actually was co-author of quite a few important things. Yeah? So for example, the frog method, he was contributing. So he's, and he's a scientist at Lawrence Livermore National Lab, and Ken Kullander also was there. Yeah, so what are they doing? They are building strong lasers over there. And why are they doing that? Well, because they wanted to build NIF for fusion research. Yeah, so it's basically weapons research. But at that time, they didn't have these intense lasers, and they used them for basic research. As far as I know, Ken Kullander was never involved in atomic weapons research, but in fundamental research like this. Okay, and here you see the same thing, yeah, but now done in helium. Right, same thing. So helium plus, right, and here helium double plus, and you see this excess yield of helium double plus quite dramatically. Right? The speculation there was shake off. What is shake off? Well, the idea there is that as you ionize the first electron, the second electron doesn't have enough time to rearrange to the new atomic states that it would have in the ion. Right? So if you peel the first electron so quickly off, then there's a certain chance that the second electron also just leaves. Yeah? That's called shake-off. So this is what they suggested in that paper. And then came the most famous paper in the field. Yeah? So in 1993 by Paul Corkum. So it says plasma, so by education he's a plasma physicist. Yeah? And this was the first paper where, well, this was perhaps not the first paper where the classical model was introduced and where the idea of recollision was discussed. Certainly not. So also the group of, so the people around Ken Kuhlander had discussed, for example, high harmonic recollision and high harmonics. But this is the first paper where basically all three effects are looked at from the same perspective. So the high harmonic cutoff, then non-sequential double ionization. So Paul Corkum's idea was, no, it's not shake off or something like that. It's that the electron returns and kicks out a second electron. Yeah? So this was his idea. And you see in figure 2, you see that he reproduced at least qualitatively, semi-quantitatively, he reproduced this thing. And so he also applied it to electrons, much to my disappointment, actually, because at that time I had just discovered the ATI plateau, but this doesn't really look like a plateau, so I was kind of okay with this paper. So very most famous paper, yeah? 5,600 citations by yesterday or so. Yeah.
So one of the ionized electrons get back to the atom and you combine and that takes another electron? Or?
No, no. So yeah, so the electron returns to the vicinity of the core, and then it may do different things. It may recombine, or it may kick out another electron, or it may, and this is the subject of the next lecture. Yeah? So non-sequential double ionization. Good, yeah. Let's continue here with the script. So we write down what the idea is. So the returning electron may kick out a second electron, or even more electrons, yeah, if it has enough kinetic energy. If, yeah, and that's natural now, if E1 max, which is 3.17 UP, if this exceeds the ionization threshold of the ion, yeah? So exceeds the ionization threshold of the ion. Yeah? This means that already at this intensity where this UP is, this 3.17 UP is high enough, you could observe doubly charged ions. And not only at intensities where the tunneling probability is high enough. Right? Now it depends, of course, also on the wavelengths. Yeah? So for different wavelengths, so if you use a larger wavelength, then UP is larger. Also, you use the same intensity. Okay. Yeah. So already at this intensity, given by this condition here, and not only at intensities where tunneling becomes likely. So already at this intensity, one can observe the doubly charged ion. Yeah, so I denote it by A2+. Yeah? So this could explain, as I said, the knee. And competing explanations would be shake off or shake up. Yeah, so shake up would mean that you excite the electron, and then from the excited state it could easily tunnel or something like that. Yeah? Or shake up. There's also the idea of the atomic antenna. I won't discuss this further. Well, ideas or hypotheses, scientific hypotheses, they have to be, well, you can't prove them really, right? You can only disprove them. And so an idea to disprove them is to look for non-sequential ionization at intensities where 3.7 UP is smaller than the ionization threshold. Yeah? So an idea to disprove the recollision scenario. This would be check if there is non-sequential double ionization. I abbreviate it with NSDE. DI. So if there is non-sequential double ionization for intensities, for low intensities, yeah, so for where the intensity is even too low, that this is so that the kinetic energy is not sufficient to ionize the atom. Okay, well, people tried that. So let's look at the slide. People tried that. In particular, so Barry Walker was the postdoc or PhD student at that time, I don't know. Kullander is also on this paper, and you see here another famous figure in the field, namely Lou Di Mauro. Yeah? And so they try to measure at lower and lower intensities, and therefore you see this curve here that previously extended here. So where is my mouse? Here's the mouse. That stopped previously perhaps here. So they went another few orders of magnitude down here. So this was a really heroic measurement. Well, and they saw that there is still non-sequential double ionization, even if 3.17 UP is not sufficient. Yeah, it's too small. And so they write a rescattering, even in the abstract, a rescattering mechanism fails to predict the observed non-sequential threshold or magnitude. So they disproved Corcom. At least they believed that they disproved him. The point is, in quantum mechanics, so in classical mechanics, it's clear. Beyond 3.17 UP, there would be not a single electron in the universe that could do that. But quantum mechanically, so we are speaking about tunneling electrons. So with real numbers, you can't make a sign larger than 1. And it's basically science that governs that thing here. But if you use complex numbers, and if we speak about tunneling, then we would have complex T0s and T1s. Then we can go beyond 3.7 UP. Yeah? Of course, the rate goes exponentially down, but on the other hand, we are here on an exponential curve. Yeah? So it's extremely steep exponential curve. Right? So this idea is good, but perhaps not good enough to disprove Corcom. Yeah? So, so there is this. So, however, even if one finds, we need the, can we switch to the script? So even if one finds NSDI for for too small E1, one could argue that in quantum mechanics, E1 larger than 3.17 UP is allowed, also exponentially suppressed. But we are on an exponential curve anyway. Well, 10 years later, so 10 years after that experiment, in my lab, we did an experiment where we used a 100 kilohertz laser. So a 100 kilohertz laser with, well, the pulse energy was not very, very large. It was just 6 microjoules. We used a 100 kilohertz laser in order to look with a more modern method, which I'll explain later, whether it's actually possible to see non-sequential double ionization in the classically forbidden region, and it turns out it's possible, right? So this is basically the proof, but you can't understand it at this point, but you will understand it at a later point. Okay, well, now the question is, are there also options to kind of support this recollision scenario? Well, there is one. The idea is the following: to look at ionization not with linearly polarized light, but with elliptically polarized light. Yeah, so with linear polarized light, the electron that returns will always hit head-on, right? But with elliptical polarized light, you also have a component perpendicular here to the major component, right? And what you induce is kind of crosswind to the electron trajectory, and therefore it will eventually miss the core, right? So one could just look at the rate of non-sequential of these multiple doubly charged ions as a function of the ellipticity, right? And this is actually what's done here. So what you see here, so let's explain first this figure here, right? So this is supposed to be the atom or ion. You ionize, then the wave packet actually disperses, right? So it's a quantum effect. And now it depends on what's the initial width, and so these things are well understood, right? And so you can calculate at which ellipticity the returning electron would miss the ion, right? And now you can plot non-sequential double ionization as shown here as a function of the ratio of these two components of the polarization ellipse, and compare it to harmonic generation, for example, also to theoretical models as shown here. Yeah? By the way, you see here another prominent figure in the field, Misha Ivanov, now in Berlin, a brilliant physicist and also a brilliant lecturer, a very funny guy. I hope he accepts at some point my invitation and gives a seminar here. Good. Well, funny thing about that paper, in this caption it cites equation 4, but I never found any equation in that paper. But actually, I also found mistakes in my own papers, so I shouldn't blame them too much for that and make fun out of that. Okay. Yeah, so this is an idea to substantiate the recollision idea. So first point here, the recollision, can we switch back to the recollision scenario can be, I can't say proven, right? It can be substantiated. Yeah? Substantiated by investigating the dependence of the non-sequential double ionization yield on ellipticity and compare it to harmonic generation or theoretical models. In the early years, the agreement that Paul Corkum claimed was disputed, but I think his opinion has prevailed. At least when I do the calculations, I come to the same results. Well, the next point would be to look at competing models, at the shake-off model, and maybe it's possible to disprove the shake-off model, right? And this is actually possible, namely by momentum spectroscopy. So disprove the shake-off model, or rather, or more generally speaking, all models that explicitly or implicitly assume that both electrons come out at the same time, right? Or pretty much at the same time. So the recollision model makes a clear prediction that the second electron comes, well, about an optical cycle, more precisely 3/4 of an optical cycle later. Right? So the first one is created at T0, and the second one a few femtoseconds, so 1.5 femtoseconds or so later, if you assume 800 nanometer light. Or 1.7, something like that. So disprove the shake-off model, or more generally, all models assuming that both electrons are both photoelectrons, I should say, are produced at the same time. So, which means delta T much, much smaller than the optical period. Right? And the key innovation to do that has to do with these three people here. Back to keynote. Has to do with these three people. Horst Schmidt-Böcking, a professor in Frankfurt, a very creative person. Then Louis Koch from Kansas State University, could say pretty much the same about him. And Joachim Ulrich, who at that time was the PhD student of Horst Schmidt-Böcking. Now Joachim Ulrich is the president of the German Physical Society, and before that he was the president of the Physikalisch-Technische Bundesanstalt, responsible for this transition to the new SI system on the German side. And even before that he was director of at the Max Planck Institute of Nuclear Physics in Heidelberg. Actually, the credit for this machine. Now I have a pointer. Nice. The credit for this machine goes, I would say, mainly. So the original ideas, I think, come from these two persons. And the decisive thing in this method is a detector, a multi-channel plate detector, as you see it here. Where's the pointer? Here, yeah. So you see, this is the sensitive area of that thing, right? It's a detector that can resolve position and time. Yeah. So you can say, if you use a detector like that, you can say at which position and at which time a fragment has hit, right? And now you can do the following thing. you can use a beam, say, of atoms, right? Ionize them. Applied is a static field, which is indicated by these rings here, right? Therefore, the electrons fly in one direction, and the ion flies in the other direction, right? So in this case, perhaps 5 electrons are ionized, produced, right? They fly to the blue detector, and, well, actually, it's the other way around here, right? So there's also a magnetic field applied. So this is a different scenario here. Yeah? So here, apparently, they fragment a molecule, right? So 5 nuclear particles. But you could also, I know that this must be the electron because of the spiral trajectory, which is due to the magnetic field. But otherwise, you could also interpret it in a way that's more compatible to the problem that we have at hand. So if you measure position and time, then you can reconstruct the momentum of the particles, the momentum of the ion core and the momentum of the electrons, right? So that's momentum spectroscopy. So, so this can in fact be done. So back to the script, please. This can in fact be done by momentum spectroscopy, and I will show how. So the idea is, if we first look at the ion, at the doubly charged ion, and compare it to the electrons that are produced. Yeah, so if you ionize such a cloud of gas, you will produce a lot of single ionization. So there will be a lot of electrons corresponding to single ionization. Right? And only a very few that correspond to double ionization. Unfortunately, all electrons look alike. So you can't distinguish which electron came from which process. And so this is much simpler if you look at the ion. You just look at the doubly charged ions. Yeah? And if the intensity is low enough, you know, they were produced by non-sequential double ionization. Yeah? So the idea is that we measure the momentum, so that we look at, that we do spectroscopy with the ion. Basically, the idea is that we apply our toolbox with with the canonical momentum. We apply it instead of to the electrons. We apply it directly to the ion. So we say, well, the electron is produced, yeah, and it's certainly accelerated. But then I also have a charged particle there, namely the ion, positively charged ion, namely particle, namely the ion, which is of course also accelerated by the electric field. Much less because it's much heavier, but still. Yeah, if I have a method that's precise enough, and this thing here is precise enough, then I can measure the momentum of the ions instead of the momentum of the electrons. Right? Okay. And if I can measure the momentum of the ion, so we want to distinguish between these two models. Why can we do that? So if the shake-off model is valid, then double ionization happens at the peak of the electric field, right? which implies that the momentum of the ion is equal to, more or less equal to 0, right? Because the momentum of the ion, according to the strong field approximation, is equal to the vector potential. And when the electric field has its maximum, then the vector potential is 0. In contrast, when the recollision model is valid, then what happens is that the electron, so T0, the electron is born close to the maximum of the field, but it returns close, it returns close to a 0 transition of the field, where the vector potential is maximum. Yeah? So the doubly charged ion is produced where the vector potential is maximum. Yeah? So this is a cool thing that allows us, well, not only to disprove the shake-off model, but to, well, support even more the recollision model. Okay. So let's write down the expected result. The expected result. So for instantaneous ionization, for instantaneous double ionization, double ionization like shake-off or something like that, most doubly charged ions have 0 momentum. Because they are born close to the maximum of the electric field of the laser when A of T0 is roughly 0. Right? In contrast, for recollision, so the return with the highest energies, so return with highest energies occurs at T1 roughly equal to 3 pi over 2. Yeah? Which means that A is close to its maximum. Yeah? And this means high momentum. For the ions. So what we expect in one case would be, so for the first case, so if we plot here, say, the momentum so parallel to the polarization versus perpendicular to the polarization, then in this case here, in this case A, we would expect perhaps something like this. Right? So most electrons, or perhaps I plot it like, so better like this. Oh no, this is also not good. Then I should do it like this and just give here the count rate. So like this. Yeah? This is what we would expect for A, and for B we would expect something like this. For the count rate. Right? So depending on the sign of the field, depending on the half cycle, they are accelerated in positive or in negative direction. Well, it's a good idea, but sometimes good ideas need hard work in order to be realized. Why this? So let's look at an example, namely at neon, which has an atomic mass of 20. Yeah? It has 10 protons and 10 neutrons, so an atomic mass of 20. And each proton and each neutron, they have approximately 2,000 times the mass of an electron. Right? So then we would, of course, calculate the drift velocity. Yeah? So we would do the usual thing. Yeah? We would say the mass of neon times its velocity at time t1, right, at the time of recollision, plus now the vector potential is equal to, well, conservation of canonical momentum at the time t goes to infinity. Now that's the drift velocity. Plus E at the same time. Right? So we know that this here is equal 0, that this is the drift velocity. And so we have that the drift velocity is now familiar formula, just we have the mass of the neon atom. Yeah? So we continue with the example by assuming that we use an intensity of 1.3 times 10 to the 15 watts per square centimeter, which is enough to induce double ionization of non-sequential double ionization of neon. So I take 1.3 times 10 to the 15 watts per square centimeter, right? And then I can calculate that UP is 78 eV, which is equal to 2.87 atomic units. Yeah? And this means that as UP is 1/4 of A squared, this means that A is equal where did I calculate that? Well, let's just write down the formula. Yeah? It's the square root of 2 UP times 2. Okay, well, now we can calculate the drift velocity, knowing that. Yeah, so what we have here is E over, now the mass of neon, yeah? And I write 40,000 times, it's 40,000 times the mass of the electron, right? I said we have 20 nuclei, each 2,000 times 20. So this thing here is equal to 1 in atomic units. Yeah, that's 1 atomic unit. And then I have the two other factors. Yeah, so I have 2 times UP, which is 2.87 in atomic units. Yeah, atomic units. And so Wie bitte? The mic is... Does it work? Yeah. So, 3.4 divided by 40,000, yeah? Atomic units, atomic velocity units. Now we need to convert this into SI units in order to get an idea, right? To get an idea of what? For what did we do this calculation? We wanted to see how challenging this experiment is, right? And we'll see it in a second. So in SI units, we would have to multiply with the atomic unit of velocity, which is the fine structure constant times c, right? This alpha times c. So 1 over 137 times c, and this gives us 180 meter per second. Perhaps it's 200 or something like that. But this is slow. In particular, it's slow as compared to the thermal velocity. Well, it's on the same order of magnitude, yeah? But we want to measure something. Yeah? So we would need to make this at least by a factor of 10, if not 100, smaller, yeah? Than this here, in order to measure it with a good signal-to-noise ratio, right? Yeah, so that's small as compared to well, it is on the same order of magnitude than thermal velocity. Now, let's look at what they did in this momentum spectroscopy, if we can switch to the keynote slide. Yeah. So actually, they use a cold beam, right? So this beam, so they use an atomic or molecular beam, which is expanded in vacuum, so supersonic expansion, which cools such a beam down, well, quickly to the single-digit Kelvin region. Yeah? So it's really cold. And therefore, one can do that, right? Okay, well, I said the experiment can be done, and it was done. Yeah, so let's see here a few names that you, or actually one name that you recognize. I think the person who had the idea for the experiment was Horst Rottke. Right? So he worked for so at some conference I was told he heard about this new method and then approached these people who used this technique of momentum spectroscopy for molecular collisions, for synchrotron experiments, for a lot of other things. I think he asked them whether they would be interested to look at the problem of non-sequential double ionization, and finally they were interested. And you see here a nice result, right? Single ionization. Yeah, so this is the momentum. Yeah, so what I've sketched here, this is basically a line out. Yeah, so if you take a cut through this, right, and the density here gives you the number of events here, right? You recognize that at least qualitatively, this reproduces exactly what is expected from recollision physics. At least what this here immediately disproves is the shake-off process. Good.
So I can't see why this proof the shape of.
Well,
I can't understand how to
Yeah. So the question is that the connection to shake off was not recognized. So I go back in my script to what I discussed here, right? So the expected result from measuring the momentum, if the process is instantaneous. Yeah, so if both electrons come out through a shake-off process, then they would come out when the electric field of the laser is at its peak, right? And at this time, the vector potential is equal to 0, or approximately 0. This means that all electrons would have, and also all ions, would have low energy, right? This is not what we see. Yeah? Conversely, if the recollision model is right, then we know that the electrons that recollide, so the electrons that recollide with the highest kinetic energy, they recollide close to a 0 transition of the electric field. And there, the vector potential is maximum. Therefore, these electrons will have a lot of kinetic energy. This is what we see. Yeah? So the experiment shows actually both. It disproves shake-off and it supports the recollision scenario. Well, we can of course calculate the expected ion momentum, right? And we do this in the same way as we did it for an electron. Yeah, so the expected ion momentum, we take a simplified scenario. Yeah, so we say, well, this the recolliding electron has just enough electron in order to kick out a second one. What does this mean? This means that at T0, there are 2 electrons sitting close to the vicinity of the core, just waiting to be accelerated by the field, right? So simplified, we look at a simplified scenario. The recolliding electron has just enough energy to ionize, yeah, so say neon plus, yeah, because we are discussing here neon plus, just as an example, right? This means we have 2 electrons with this velocity T1 is equal to 0. Well, and of course, also the ion, as a neon double plus, has this velocity, right? And so we do conservation of canonical momentum, and what we find is, so we would say, so we would write here neon 2 plus and its drift velocity, that this is equal to 2 times A of T1. Why 2? Because it's doubly charged. Yeah, and if we do the calculation for the above numbers, then we find something like 7 atomic units, momentum units. Well, what they found was a little bit less. So if we go back to the measurement, then they found actually a little bit less. Right? So perhaps something like 5 or so. Right? But of course, we look here at a simplified scenario. How precisely they were able to measure the intensity is another open question. Right? So this is always a problem. And as I said, so this here is just the cutoff, and here they have the full picture. Actually, as indicated here in this picture, one can also measure the electrons and the ions in coincidence, right? Then this problem that I indicated in the beginning, that we have a lot of singly charged ions, that we have to discriminate against the doubly charged, the electrons coming from the doubly charged ions, then this can actually be done, right? It means that in most laser shots that we do, we indeed would see single ionization, just a single electron, right? But in some, we would see actually a doubly charged ion, and perhaps 2 electrons. Actually, we don't even need 2 electrons. 1 would be sufficient, because via momentum conservation, I can reconstruct the momentum of the second electron, right? So for the experiment I discussed so far, only this arm here measuring the ion was sufficient. But of course, also both can be done, and it has been done by the group of Reinhard Dörner. He in some sense is the successor of Schmidt-Böcking, and they are doing wonderful experiments there. And this was the first in this row connected to laser physics, right? So they looked for the electron, and what they plot here is the momentum of one of the electrons, and on the other axis, the momentum of the other electron, right? And if it's right what we said, then both electrons should go in the same direction, should have the same momentum, right? This is what you kind of see here, right? So there are also a few events here. So this was done here, I think, with argon. With argon. There are also a few events that don't fit to this picture. But the majority, they do fit, right? And here they go in the opposite direction. If they would increase the intensity to a region where sequential ionization dominates, there's no correlation. There's no correlation between the electrons, as you see from this more or less isotropic distribution. Okay, well, it took me much more time than I expected to cover non-sequential double ionization, so it will be only next week that we discuss the third option that the electron has. Right? So the first option was that it recombines. The second option was inelastic scattering, that it kicks out the second electron. And the final one will be elastic scattering, that the electron scatters off the field without changing its kinetic energy, only changing the direction of its velocity. Thank you for your attention. Jo.